to the first 9 between Houdini tutorial. In this tutorial, I will be showing you how to create this Phoenix disintegration effect. This will be a 4-step process, with step 1 being to create an infection solver. Step 2 will be to fracture our geometry. Step 3 will be to transfer that infection attribute back onto our geometry. And then finally, step 4, we'll use that to disintegrate our geometry. Alright, in Houdini, let's begin by dropping down a geometry node, dive inside and delete the file node. We will just create some basic geometry to use so that everyone can follow along, and at a later stage we'll introduce that custom animated geometry that you see in the intro. So drop a torus and a transform, and on the x-axis, let us rotate this torus by 90 degrees so that it is upright. Alright, now at frame 1, let's hold Alt and click Translate on the Y, scrub to frame 120, hold Alt, click on Y Translate, and we'll set that to 5. That'll give us a simple animation of our torus moving up. To add some interest to this, let's simply put a piece of code over here as $ff times 2. And what that will do is, at every frame, it will take the frame number, multiply it by 2, and set that as our Y rotation. So as we can see here, at frame 48, it has 96 degrees of rotation. Alright, we can drop a time shift node, delete the frame channel, and set it to 1. Now, at every frame, it'll hold the first frame's animation. Drop down a scatter node next, connect that to our scatter, and we'll set this to 10,000 points. Duplicate our scatter, and set the second one to 1 point. So these will be our points to be infected, and the single one will be our initial infected point. So drop down a group create, and we'll set this to group type points, and rename this to spread underscore grp for group. Drop down a merge node and merge these two streams together. Now we should have 10,001 points, with one of them being in the spread group. Alright, in an attribute wrangle, we'll simply initialize a spread attribute. So it will be an integer at spread equals 0. Now every point has this spread attribute initialized at 0. We can now begin on our solver. Dive inside the solver and just delete all of these object merge inputs. And we'll just be using this previous frame. So drop down an attribute wrangle, and into our first input, we'll connect this. Alright, holding Alt and E will bring up our string editor, and we can now begin on our algorithm. So to start with, we need to initialize a few variables. Firstly, int PTS, which will be all of the points near currently infected point. And that will be an array. So vector pos, this will be the current position around which to check. Int max PTS, we'll make this a channel integer called max underscore PTS. And that will be the maximum number of points to add to our array around our position. Next, we need a float called rad, which will be radius. And that's a channel float, and we'll simply call it radius. And that will be the radius around our pos to search for a max number of points to be added into our PTS array. So we would like this to do the following. If the currently processed point is in point group, then do the following. So firstly, we need to set up our in-point group function, and that requires 3 parameters. Firstly, our geometry stream 0, the group that we need to check for, which is spread underscore group, and the currently processed point, which is at pt_num. Now this will return a 1 or a 0, and that will determine whether a point is currently in our spread group. So if the currently processed point is in spread group, then do the following. set the spread attribute to 1 for that point, set our pos that we initialized up here to the currently processed point's position at P, and our array needs to be set up with all of the points near to this position. So we have this function near points, which is going to use geometry stream 0, our current position of our point, and it needs to search this radius for this number of points. Finally, we need to have for each of the points inside of our array added to the infected group. So int pt, pts. So for every point inside our pts array, do the following. Set its point group, and this will take geometry stream 0, spread group, and pt, which is the currently processed point. And this will be a 1 or a 0, 1 being in the group, 0 being out of the group, and set. So if we apply and accept, shouldn't have any issues. And let us just click this to create our spare parameters. Set our radius to 0.1 and our max points to 5. And now make sure to set the display flag onto your attribute wrangle, or else this won't work when you jump up. So jump up a level, and we'll drop down a color node. This color node we'll just use as a visualizer, so we can just call it viz. And it needs to run over only our spread group, so points in the group will be changed to a red. Now if we play this back, it should work. And I do believe that this is a problem with the scene view. Yes, there we go. And now we have these points spreading over our torus. And if we play this in real time, it works. And you can increase the speed of the spread by changing your radius and max points. So now we have this torus that's infected, but we've lost our animation. So to reintroduce our animation, let's drop a point deform. And point deform takes 3 inputs. The first input is what we would like to deform, and we would like to deform our points. So connect that into our first input. The second input is a static geometry, and the third input is that geometry but animated. So we have all 3 inputs connected, and now if we play it back, we'll see that our torus is animated and has our spread solver working. Alright, now that our infection solver is completed, we need to start working on the fracturing. To do our fracturing, we'll drop down a voronoi fracture and a scatter. Plug our timeshift into our scatter, and plug our timeshift into the first input of our voronoi fracture. Plug our scatter into our voronoi fracture second input, and we can set the display flag on there. Now we can see it's fractured, and if we drop an exploded view to visualize, we'll see that it's worked. However, we don't want these interior pieces, so what we'll do is we'll simply go to our voronoi fracture and disable create inside surface. Now, the reason that we use this time shift is because if you were to connect your animated geometry to your voronoi fracture, it would refracture at every frame. And that runs extremely slowly. We can test that by doing this. And that doesn't play in real time. So rather connect your time shift here and your time shift there, and then use another point deform to deform it. So what we want deformed into the first input, our static geometry into the second, and our animated geometry into the third. And now it plays back in real time. And as you can see, it is still fractured. Alright. Next, we need to transfer the spread attribute from our point deform onto our fracture. To do this, we will drop down an attribute transfer. and connect our voronoi fraction to the first input and these points into our second input. Simply set our spread attribute to be the attribute to be transferred. And now as we play this back, you will see that it is gaining the spread attribute. And to visualize this, we can simply put our CD there as well, which is our color, and we'll see it spreading onto our torus. Great. So the next thing to do is to simply create a group that tracks which points are currently infected. So we'll say if at spread greater than 0, then put these points into a group, set point group. And this takes geometry stream 0, and this is a new group that we'll create called released underscore GRP. And then we need to take the currently processed point at pt_num. We want it to be in the group, so that's 1, and then set. All right. So next, we'll drop an assemble node and create a packed geometry. The solver that we're going to be using is the RBD packed objects, and this requires packed geometry. However, when you pack geometry, you lose your attributes. So we'll simply transfer the attributes back on by putting a star, which means all attributes, into our transfer attributes box. There we go. Now, what this assemble does is it takes all of our points, or each primitive, and sets it as 1 point. So if we drop down an exploded view and visualize points, we can see that before we had all of these primitives with multiple points, but after our assemble, we have all of these primitives, each one being a single point. All right, and we'll duplicate this attribute wrangle that's above our assemble and drop it below again, because now we want each one of these points to do the same thing. We are almost done here. We'll just drop down an attribute wrangle, and this wrangle we'll use to set up all of the parameters that will be used in our solver. So I at deforming, we'll set this to 1. F at mass, we'll set this to a channel float so we can control it. Let's call it mass. And finally, F at density, which we'll set to 0. Click here to create our mass parameter, set that to 10. So to explain what we've done here, I at deforming simply tells the solver that all of our points are animated, they're moving, they're deforming. If this was 0, it would mean that they're not deforming. Next, we have our mass, which we've set to 10. Mass is multiplied by density to give you your mass value. So a mass of 10 multiplied by 0 will give you a 0. And if your mass is 0, then all of these will not be affected by forces. Simply, they'll only be affected by the animation. So this torus will rise and spin as it has, but it won't be affected by wind or gravity because it has a mass of 0. Now, in our next attribute wrangle, our released points, we would like those affected by forces. So we will choose our released group, which we created earlier. And in this group, we'll set our deforming to 0 because we don't want that to follow our animation anymore. And then we'll change our density, F at density, to 1. And what that will do is, as a point is released, it will no longer be deforming. So it will no longer follow animation. And it will now have a mass, so it will be affected by forces like gravity and wind. So if we jump up and drop a dot network, and just to make this easier, let's drop a null and connect this to our null, and we'll call this out geo, just to make it easier to reference. So dive into our dot network, and we will drop down a few things. Drop down an RBD packed object, a rigid body solver, gravity, and wind. And we'll just connect these. So now our RBD packed object needs to search for our out geo, and that will be our stop path. Now we need to overwrite a few attributes. The attributes that we need to overwrite would be deforming and mass. Great. And now, if we play this back, we'll see that as it spreads to those points, it starts breaking away. And that's exactly what we want. So as the points break away, they no longer follow the animation, and they are affected by our gravity and our wind force. And if you like, you can mess around with all of these settings to change the wind to how you would like it. But simply, there it is, breaking up. Right here I have the Phoenix file opened, and as you can see, it's the same setup, but we have this object merge, which brings in the Phoenix, and it's just transformed down because the Phoenix is massive, and then we have it fed into the same setup. So this is that network, the infection or propagation network, and as you can see, the only difference is the scatter node has been turned into this add node. And if we take a look at that, it is 3 points. They just spread one over there, and one at the tail. And if you check where those are scattered to, it's scattered to the wingtips and the tail tip. And so what that does is it starts our propagation or infection from those points. So we have more control over where it starts. And so, as you can see here, here is our visualizer for our spread, and it spreads all over. And when we use the point deform, same as before, except now we're using custom animated geometry. And this just gets fed into the exact same setup as before. And then we go up a level to our top network. And as you can see here, it's still the same. So the only difference is once all that's done, I cached it out, unpacked it, and applied its materials onto it. And that gives us that Phoenix that you see in the intro. Alright, that's it for this tutorial. And all of the links are in the description. The link to this Phoenix geometry, which is done by Norberto 3D on Sketchfab. It's free to download. All the links are in the description, and if you would like to check out the documentation that's used in the VEX code that we've done, it's all on the Houdini website.